Okay, hello everyone. Thank you for the introduction, and I thank the programming committee for this opportunity to present a tutorial on multi-wavelength techniques in digital holography for applications in surface profilometry. I'm sorry, I'm not able to participate in person, and I hope I should be able to see many of holography friends and colleagues in person next year. First, I'd like to acknowledge all the students, postdocs, and collaborators, as well as the funding sources for making this line of research possible over the years. I think I should hide myself. I think it is blocking part of the slides. Okay, so digital holography reconstructs both the amplitude and phase of the optical field. And as shown in one of the first quantitative phase images by digital holography here, the phase profile reflects the optical height or thickness profile, and therefore it can be used to acquire such surface profile. On the other hand, when the optical thickness is more than a few wavelengths, as in this image of cancer cells, the phase profile contains 2π discontinuities. In this case, one of available numerical unwrapping algorithms was used to remove such discontinuities. Numerical unwrapping is usually based on detection of discontinuities and can be subjective and non-deterministic. It can run into difficulties if the phase profile is more complicated, noisy, or has large phase jumps. Multiple wavelength optical phase unwrapping offers an alternative approach based on synthetic wavelength that can be much larger than the single wavelengths. Today, I'm going to describe and compare three related multi-wavelength phase unwrapping methods that I'm referring to as the hierarchical optical phase unwrapping, cumulative optical phase unwrapping, and digital interference holography based on synthesized optical low coherence. It turns out that the multiple wavelengths can be generated not just by actually using different laser sources, but also simply tuning the illumination angle using a single laser, which can significantly reduce experimental cost and complexity. So we start with optical phase unwrapping using two wavelengths. Suppose we take two holograms using two wavelengths, λ1 and λ2, and combine the two reconstructed fields, E1 and E2, as E1 times E2 conjugate. Then the difference phase, phi12, is 2π times the height profile divided by a synthetic wavelength λ12, which is given by λ1, λ2 over λ1 minus λ2. If the wavelength difference is small enough, then this synthetic wavelength λ12 can be made larger than the maximum height in Z. Then the height profile Z12 measured with the synthetic wavelength λ12 can cover the height range of plus minus λ12 over 2. In this simple simulation, The object is an incline of maximum height 15 micron. If a single wavelength of 0.635 micron is used, then the phase profile has many discontinuities. If we combine with another wavelength, 0.6 micron, then the synthetic wavelength is 10.9 micron. And the new height profile covers that much higher range. On the other hand, if we assume about 3% of noise in each of the single wavelength phase profiles, the synthesized height profile also has 3% of the maximum height, or square root 2 times 3% to be more precise. So initially, the single wavelength profile has about 0.02 micron height noise in here. But the synthesized profile has noise 0.46 micron. The height noise is amplified in proportion to the synthetic wavelength. The amplified noise can be reduced if we generate another shorter synthetic wavelength, lambda 1.3, using a third wavelength, lambda 3. So if we use lambda 3.53 micron, then lambda 1.3 is now 3.2 micron. Quite smaller compared to lambda 1.2, 10.9 micron. Now the new profile has more discontinuities, but this Z13 is stitched onto Z12 using Z12 as a guide. That is, we divide Z12 by integer multiple of lambda 1.3 like this, and we paste these segments on top of this to obtain this Z prime 1 to 3. And this phase profile has much less noise compared to Z12. In fact, it has the same level of noise as Z13, except for these spikes of height lambda 1.3. And this is because of the noise in Z12, and this boundary between the integer multiples has these glitches. The spikes can be removed by comparing Z12 and this Z prime. And if the difference is larger than some fraction of lambda 1.3, then lambda 1.3 is added or subtracted depending on the sign. And this is possible only if lambda 1.3 is significantly larger than the noise in Z12. Only if this is large compared to the noise in Z12, which leads to the requirement that the stepping factor alpha, given as the ratio of lambda 1.3 over lambda 1.2, to be fairly large compared to the noise level epsilon. So if as long as that condition can be met, the process can continue. So if you apply that procedure, then the final unwrapped profile has a much lower noise without these spikes. And this process can continue in hierarchical manner by choosing progressively shorter synthetic wavelengths lambda 1n, while keeping the requirement on the stepping vector alpha. Here we start from lambda 1,2 equal to 2000 micron and go down to 31 micron using 5 wavelengths. The noise is reduced from 78 micron to 1.2 micron. The hierarchical phase unwrapping principle was first demonstrated by Austin et al. Using a tunable dye laser and acquiring holograms at 4 wavelengths with stepping factor 0.5. They have profiled an object a few millimeters high with noise in the small fraction of millimeter range. This is another example of hierarchical OPU experiment where I have used 4 discrete precision-tuned DPSS lasers at these wavelengths. And the field of view is 24 by 24 millimeters squared. The corresponding synthetic wavelengths were 19.75 millimeter, 5.3 millimeter, and 0.6 millimeter, where it turns out that the last synthetic wavelength, lambda 1,4, is too short. That is, the alpha stepping factor between these two is 0.11, which turns out to be too small. And one can see that the noise in Z12 went from 0.92 to 0.56 millimeter, but the last one, Z124, has no improvement over Z123 because the alpha was too small. Okay, this is same data in cross-section. And this is an example of the surface profile of a coin from the same experimental setup. Now, instead of using multiple lasers or a tunable laser, a similar effect of multiple wavelength generation can be achieved by scanning the illumination angle of the object surface. For a given optical height z, the optical phase along the angled path z prime is 2 pi z over lambda cosine theta, which is equivalent to saying the effective wavelength is lambda times cosine theta. So the effective wavelength is given by lambda times cosine theta, and this angle scan system can be much simpler, economical, and flexible compared to actual wavelength scanning system. Also note that because of the cosine dependence, one starts with a bias angle theta 0 at some tens of degrees, so that the effective wavelength change is not too small. Near small angle, when theta is very small, near 0, then the cosine barely changes, and therefore the lambda theta barely change. So this finite bias angle can lead to some shadowing effect, especially if the object has tall, abrupt edges. This is an example of optical configuration for angle scanning holography. The input mirror M1 is mounted on a digital controlled rotation stage And the confocal lens pair L1 and L2 image the rotating mirror on the object plane, which is also optically conjugate with the reference mirror and the camera plane. This way, the rotation of the input mirror changes the object illumination angle without changing the relative angle between the object and reference. In this example, a set of three mirror-like surfaces are imaged using 8 illumination angles. The first two effective wavelengths, here and here, are 0.05 nanometer apart. By changing the angle by 0.0014 degrees from 18-degree bias, which gives overall range of lambda 1, 2 equal to 7.5 millimeter. By reducing the synthetic wavelengths with stepping factor alpha equal to 0.5, the last synthetic wavelength lambda 1, 8 is 0.115 millimeter. The measured surface noise reduces from 127 micron to 3.5 micron. And this is a cross-sectional view of that previous data. And this is an example of coin surface with the same setup using 8 effective wavelengths. And you can see the significant reduction of noise from profile ZZ12 to ZZ128, using 2 wavelengths down to 8 wavelengths. On the other hand, if we just use 4 wavelengths, to reach the same final synthetic wavelength, 44 micron, 4 wavelengths instead of 8 wavelengths, to reach the final synthetic wavelength 44 micron. That is, if we use alpha equals to 0.125 instead of 0.5, then the alpha turns out to be too small, and the noise reduction process fails, as predicted. Here are several examples of surface profiles acquired using wavelength scanning or angle scanning, hierarchical phase unwrapping, which shows that fairly good quality surface profiles can be obtained using these techniques. I want to note that I have attempted to use some of the conventional image processing techniques, such as windowed Fourier transform, total variation denoising, block matching and 3D filtering, etc. But apparently these methods do not apply well to the particular type of noise here. And these images have used only the median filtering to improve the visual quality. Okay, so now to introduce the cumulative unwrapping method. Note that on the inverse wavelength axis, 1 over lambda n, for the hierarchical method, the inverse wavelengths are chosen at geometric intervals with the common ratio of 1 over alpha. So when alpha is 0.5, you have 1 unit here and 2 units and 4 units and 8 units and 16 units. The first interval, lambda 1, 2, or 1 over lambda 1, 2, given by 1 over lambda 1 minus 1 over lambda 2, determines the height range that can be profiled, while the overall range in inverse wavelength, 1 over lambda 1 minus the last one, 1 over lambda n, this range determines the final height resolution. On the other hand, in cumulative OPU, the inverse wavelengths are now chosen at uniform intervals throughout the range between 1 over lambda 1 and 1 over lambda n. So this entails acquisition of much larger number of holograms. But COPU, cumulative OPU algorithm, turns out to be much simpler and and is less prone to phase noise because of an averaging effect. So from the n holograms taken at uniform intervals of inverse wavelength, take the difference phases, phi1 minus phi2, phi2 minus phi3, phi3 minus phi4, etc., and sum those differences. Then the synthetic wavelength between these pairs is all equal to the same lambda 1, 2, denoted lambda here, common lambda here. And the final phase profile is just n minus 1 times 2 pi z over lambda. And if we require that this synthetic wavelength, lambda, be larger compared to the maximum height we want to profile, then each of these underlined terms will not need modular operation or have no discontinuities. So the height profile z obtained from this psi is given by this, and it covers the range plus minus lambda over 2. And the noise in this profile is also reduced from the noise of z1, 2 by the factor n minus 1. All right, so this is a comparison of noise reduction between hierarchical OPU and cumulative OPU. In HOPU, 5 wavelengths are used to reduce the synthetic wavelength from 2000 micron to 31 micron. While in COPU, it took 65 wavelengths to reach the same final synthetic wavelength. And both cases yield similar level of final noise. Ladle et al. Has demonstrated what they refer to as frequency sweeping digital holography using a tunable diode laser, sweeping over a few hundred frequencies and achieving measured height of 12.5 millimeters with good image quality. They have also demonstrated the angle sweeping digital holography for tympanic membrane measurement application. They have achieved 1.5 millimeter height range with 0.14 millimeter resolution using 9 effective wavelengths. Okay, so on to the last of the three methods. It turns out to be possible to process the same data set from cumulative OPU in a different way. That is, take the series of holograms using a uniform series of K or 1 over lambda to form a 3D stack of holograms. Then take FFT of the stack with respect to the K-axis, which will then yield the tomography or topography of the object volume. And Z range of this object volume is then determined by the delta K step, or step in 1 over lambda. And the Z resolution, again, is determined by the total scan range in 1 over lambda, which is really equivalent case as with the cumulative OPU. So in this demonstration of wavelength scanning digital interference holography, a ring dye laser was used to scan 30 steps at 1.06 nanometer intervals, starting at 575 nanometer. These show about 1 by 1 millimeter squared areas of a penny, and compound eye of a wire end. Angle scanning instead of wavelength scanning is also possible here as well, as shown in this demonstration by Hong et al. Of a 1.8 micron standard step heights using 100 holograms at 0.04 degrees steps. And similar methods have been used more recently, one by Dong et al. Using rotating mirror for n equals to 15 steps to achieve 0.8 millimeter range. And here they have used an SLM for angle scan with n equals to 17 to achieve 46 micron range. So here I have processed the same data set for cumulative OPU and digital interference holography with n equals to 100 and synthetic wavelength ranging from 7,500 micron to 75 micron. They yield similar results, as you can see in these profiles, but one may be more appropriate over the other depending on applications. The DIH is a tomographic method based on low coherence synthesized by the frequency diversity. On the other hand, the COPU is a phase profiling technique, and as such, it produces single-valued function over a two-dimensional object surface. This means that the tomography is not possible with COPU, but the topography can potentially have higher resolution than DIH. So to summarize, I have given an overview of three techniques for multi-wavelength holography, for surface profilometry, hierarchical OPU, cumulative OPU, and digital interference holography. COPU requires much larger number of holograms than HOPU, but the algorithm is simple and straightforward and can have better visual quality because of averaging effect. Similar data set as COPU can be used for DIH, which can have distinct advantages and applications. So, thank you. everyone for your attention.